Hi, my name is Wenzong Huang, and I'm an undergraduate student from the National Taiwan University. So in this work, we are demonstrating how we apply custom RISC-V instructions to mobile AI applications. So in AI algorithms, convolutional neural networks are commonly used for visual feature extraction. Typical applications include image recognition, object detection, and semantic segmentation. However, convolutional layers require high computational complexity, so an efficient RISC-V core and accelerators are necessary. With RISC-V strengths in extending instructions, we are able to explore multiple configurations and evaluate their hardware performance in a wider design space. The CPU core we use here is the Andis N25, and an assistive tool called Copilot is used for program profiling, enabling fast evaluation of hardware performance, such as cycles, area, and energy. Here, we use 2D convolution accelerators with different channel partition parameters and evaluate their cycles area. In this figure, we can clearly observe the trade-offs of these configurations, and we can then select the optimal solution for our design target. We thank Andis Technology and TSRI for technical support. Thank you.
Hello, everybody. Let's talk about the verification of the RISC-V. So the talk about is how we get unbounded results using formal verification of RISC-V CSRs with interval property checking. Functional verification of RISC-V cores. This is not an easy task, and has to answer the question, does the RTL precisely implement the RISC-V ISA? So RISC-V cores processors are hard to verify. Complex microarchitecture to achieve PA targets. There is branch prediction, there is forwarding, there is out-of-order execution, etc., etc. And formal verification is the only technology that can prove absence of bugs. So the biggest challenges are that complexity issues lead to bounded proofs. There are hard to write, good quality, reusable assertions, because the level of configurable of these cores is so high. So there is 32-bit, 64-bit, there is different extensions and so on. I mentioned that interval property checking, so giving you a brief introduction of what is interval property checking. So an interval property checking is an assertion that does not start from reset, but from a generic valid state. And it has a limited number of cycles to reach generic valid state. And it decouples ISA spec requirements from microarchitectural details. So application to in our project is to the RISC-V rocket core. In the poster session, it shows different details on how the CSRs are verified using the interval property checking. By verification of CSRs, I mean there is the case like instruction updating the CSRs, like raise exception instructions, like interrupts, debug, and exceptions that can occur, and errors. So this, as I mentioned, this work with verification of CSR is part of a comprehensive solution from OneSpin, RISC-V integrity verification solution. This proves bug absence for the entire core, proof absence of hidden and malicious logic. So feel free to join the poster session me and I'll answer every question. Thank you.
今天晚上我给大家讲的是这个 Coreboot for RISC-V Freedom 固件自由，然后这个主要说一下这个 x86 下面的这个固件的问题啊，然后介绍一下这个 RISC-V 跟 Coreboot， 主要谈一下那个RISC-V 的那个机器结构跟那个 Coreboot 这个RISC-V 的这个代码的一些架构，然后讲一下我移植的一些经历， 我搞过那个 HiFi One，那个是硬编码的，因为它那个资源有限没法做，然后还搞过一个那个 HiFi One Initial， 这个现在可以跑 Linux， 社区版本不可以跑，我们把它放在我们自己的那个 GitHub 上面，就这些，好，谢谢。
So we believe that silicon proof everything is ISA. So we came out this SoC chip December last year on 55 nanometer. The chip is on the rocket chip architecture. The configuration is RISC-V, IMCF, 64 bytes iCache and 64 bytes DVI. We have some communication ports like GPIO, IC203, SPI, UART, and also we can use QSPI flash to do the program management. And also, before the chip came out, we have 14 artist-wide autos on our FPGA development board. So the question is why we use rocket chip architecture. We have do some evaluation on this code for over 1 year. We think it has very many well-defined subcomponents and good extensibility for architecture evolution. And most important thing is the rocket chip can help us to reduce our project design cycle. We spent only 1 month to develop the chip when we decided to do this project. And we think the performance of the rocket chip architecture is not good as we want. In fact, our customer need us to do the optimization. So the next step, we will do some performance optimization and do the vector extension implementation. Integrated AI accelerator. We will do tape out again at some server this year on 28 nanometer. And also some other line on our roadmap. Okay, thank you.
Hello, my name is Kisan Nagara from the University of Telecommunications in Japan. We have developed the 64-bit RISC-V chips with new A1 empty memories and some peripherals. The objective of this work is to show that even university students can develop the RISC-V chip in a very short time by using the open source RISC-V SoC or FPGA design environment. This slide shows the block diagram of the chip we developed. We used the Sci-Fi's freedom platform as base design, and we modified and added some green boxes in this diagram to the original design. And this is the implementation result of the chip. This chip is fabricated by using the shuttle service of the ELSI Design and Education Center, in Japan. And we evaluated this chip and confirmed it operates as we expected. And thanks to the Sci-Fi's open silicon platform, we could design this chip in less than a month. Thank you.
So I'm from a company called Calber, for whom not yet know about us, since we just come up from silent mode and the last year. We are a processor IP company based on RISC-V, and since established in 2015, we were more focused on high-performance RISC-V machines, which lead to our out-of-order product, which is called PI671. And in meantime, we built also power-efficient version, which is in order BI651, which is comparable with mid-range well-known ARM cores. And just a couple of weeks ago on Embedded World 2019, we released Tiny Lens application for IoT applications. We as well are ramping up our microcontroller series, and first core available and already shipping to customers. In that series is a microcontroller core called PM310 with full toolchain and ED environment available for customer needs, starting from our own IDE based on open source toolchain and including third-party products like Cloud for Buttons. And thank you very much. If you like to know more about our course and benchmarks, please come to the poster slide. I will answer your questions. Thank you.